Hello everyone, welcome to week 7 of our course on Foundations of Deep Learning Concepts and Applications. So far we have travelled through some of the important building blocks of deep learning, where we have covered in the week 1 and 2 we have seen artificial neural networks. Week 3 and 4 we have seen convolutional neural networks. Week 5 we have explored explainable AI, and last week week 6 we have seen CNN based segmentation and CNN based object detection algorithms. All of these we have explored so far through hands-on learning. Now in this particular week, let us look into sequence to sequence models. Now let us get into the concept sequence to sequence models, and under these we will be mainly focusing on these three algorithms. We will look into recurrent neural network RNN, and then a long short term memory LSTM, and gated recurrent unit GRU. So the contents for this particular week, that is week 7, are as follows. First, we will understand what exactly is a sequential learning problem. Then we will look into the introduction to RNN, where we will be focusing on the architecture of RNN and what all the different types of RNN we have. Then we will solve one numerical example. We will go into step by step how exactly the forward computation takes place in RNN. Then once we solve a problem, once we get into the forward computation, then we will see how exactly the back propagation takes place in RNN, that is backward through time, back propagation through time. Then there are we will look into the challenges in RNN, training the RNN, such as vanishing and exploding gradients. Towards the end of this particular week, we will see the hands-on implementation of RNN using Keras, and we will take an example of a time series problem. These are the contents for this particular week 7. In the coming week, that is week 8, we will explore LSTM and GRU with the hands-on. So these are the topics for today's session. So in today's session, we will understand, so far we have seen ANN and CNN. Why not use ANN and CNN for sequential data? Why ANN and CNN structures fail for sequential data? When we say sequential data, what exactly mean by sequential data here? Now look into this particular example. It is predicting the temperature. Here we have a sequence of 6 days temperature we have the last 6 days temperature with us. Now with this we want to predict what is tomorrow's temperature. So tomorrow's temperature depend on the sequence of the past temperature values. Similar way, very popularly what we will be doing on a day-to-day basis, when we are typing anything in Google, always Google predicts the next word based on the sequence and based on what you have typed before. So whenever this is an example for sequential data. Whenever we have a data of this kind, whenever our problem statements are of this kind, why CNN and ANN structures fail to solve this? First, let us try to understand that in today's session. Then once we are familiarized with this, once the concept is clear, then we will learn the RNN architecture. Then how RNN remembers the previous input while processing the next one using a recurrent connection. And towards the end of this particular session, we will also discuss what all the different types of RNN we have. So with this, let us get started. Our first point of discussion is why ANN and CNN structures fail for sequential data. Let us learn that, or let us try to understand. So this is what is the data set that we have already seen. It is a popular IRIS data set. And if you look into this data, there are totally 4 features. Because there are 4 features, so 4 values are being passed to the first hidden layer. 4 features are passed at the to the first hidden layer. Then we have 2 hidden layers that are built, and this is an input, this is an hidden layer. And if you look into, since it is an multi-class classification, you have 1, 2 and 3 different classes. Therefore, we have 3 neurons at an output layer. And the 3 different classes here are Sotazo, versicolor and virginica. Now, this is the architecture that we have built for this particular data set. Now, if you look into this, entire training data, every sample is of fixed length. Now, if you look into what do you mean by fixed length, the first sample, this is a sample 1, sample 2 and so on up to sample n. The first sample is of length 4, second sample is of length 4, last sample is also is of length 4, which means feed forward neural network always expects the input to be of fixed length only. So, feed forward expects fixed length input vectors. Now, during a training, the model has learnt with 4 features. Now, during a testing, can we just pass only 3 samples, only 3 features? No, right, it is not. So, always feed forward neural network expects the data to be of fixed length input vectors. To that matter, even during a training also, we expect every sample should be of fixed length. So, that is one mandate requirement. During a pre-processing, we are going to take care of this point. Now, once the model is been trained, now what we will do? We will now pass one sample. When a sample is passed to this trained neural network, the model is going to do one prediction. We are going to get a prediction here. Then you will pass the next sample, next input sample during a testing. Even when you pass this, the model is going to do a prediction for this. Now, when you pass one sample, the model is not at all looking into what the previous input was, how the previous input was, what was the prediction made for the previous, how the previous input is. The model is not at all looking into. You pass one sample, the model gives the prediction. You pass the second sample, the model gives the prediction. Now, you are passing this input, so you get the prediction here. Now, when you pass these set of samples, the predictions are made for each of this. So, the second important point that we need to consider here is each input sample is treated independently in feed forward neural network. What do you mean by treated independently? During a training phase, if you look into during the training phase, all the samples have been learned independently. How it is learning? It is just seeing the first feature and it is mapping x and y. If all these are considered as x, if this is considered as y, it is just learning the mapping between x and y. Here it is learning the mapping between x and y. So, every of the sample are learned independently here. And during testing, the predictions are made purely based on the current input only. What input you pass, for that the prediction is made. When the prediction is made for the current input, feed forward neural network is really not looking into what was the previous input. So, this is how the feed forward neural network was working. So, what exactly it is happening? So, it processes each row independently, yes. It does not remember what the model has seen before, yes. It really does not care about the order of samples. What does it mean? Here, if you look into whether the first row 1 is coming first, then row 2, or whether row 2 should come first, then row 1, it is really not bothered about it. So, feed forward forward neural network does not care about the order of samples also. Therefore, there is no temporal and or a sequential relationship between the rows of data. So, 3 important points that you need to focus or remember from this particular slide. When you are processing or when you are working with the ANN model, always ANN expects the data to be of fixed length input vectors. Second, it treats each of the samples independently. And third, there is absolutely no sequential relationship between the rows of the data set. The same thing applicable even in CNN as well. If you look, this is what is the convolutional neural networks CNN, and if you look here, all the input, this is an input that is passed to CNN model. Now, when before you pass the input to the CNN model, if you remember from week 3 during the hands-on, we are going to bring all the samples to a fixed length. So, in CNN also the size of the input is always fixed, that is all the images are resized to a fixed shape before actually the data is passed to a model. If you recall, during the pre-processing step itself, we are going to bring down all the samples, training samples and testing samples to a fixed length. We used to define a target shape, and whatever is the target shape that we define, all the samples of the data set will come to that particular one. So, which means the input to CNN is always of a fixed size. Next, what is the second characteristic? Any input, when you pass zebra input to CNN model, now when this input is passed, convolution is going to extract these features, then flatten, then a dense layer is going to classify this as zebra. When you pass dog image, the entire convolution layers first extract the features of the dog, then dense layer will learn how to classify this as a dog. Similar way with the horse. What we are trying to say here is, during a training, each of the samples are being learned independently here as well. So, CNN also treats each input independently. So, the images, each image is processed independently, which means during a training the images are learned independently, and during a testing, suppose you are passing an horse image, the model is going to predict horse. If this is a zebra, this is a dog, this is a horse, then let me erase here. If this is horse, then if this is treated as a horse, then when you pass a horse image as an input, then you will see that this value will be very high. Similar way, when you pass dog as an input, we will see this value very high. So, what we are trying to understand from this is, during testing also, the predictions depends only on the current input, but it never bother about, okay, previous I have seen zebra, now should I predict it as, no, it never depends anything on the previous input. So, this is what how CNN works. What exactly are the problems with the forward neural network and CNN? So, the problem, the following are the 3 problems. The model reads each input independently, yes, and then there is absolutely no dependency between the inputs, and it expects the input to be of fixed length, and there is no temporal or sequential relationship between the inputs. This is how ANN and CNN processes the input and then the working mechanism. Okay. If that is the case, let us consider the following examples. Let us look into this particular example. What is this? Now, there is an shop owner, and the shop owner wants to predict what will be the Monday's sale. Here the shop owner wants to know what will be the Monday's sale. If if owner has to understand this, the owner has to look into all of the previous trends, how the particular item is being sold, when the item is getting sold, which are the days. So it has to look into all of the previous patterns or the trend. Therefore, in order to predict the Monday's sale, actually the prediction here depends on the sequence of past values. If you have to get this value, it depends on this particular sequence, right. So here with this, what are we understanding? Inputs are dependent on each other. In this particular example, input is actually dependent on each other. So this is a time series example where yesterday's sale actually affects today's sale. One more example, we can take a stock market prediction or weather forecasting. If you want to know what will be tomorrow's temperature, it actually depends on the last 1 week how the weather is. So if you can know how for the past 6 days this is how the weather is, with this you can predict what will be tomorrow's temperature. So if for this kind of an application, here the input is actually dependent. In order to predict tomorrow, it is actually depending on the previous. So this is what is an example for time series. Now let us look into this particular example. What is this example? You have passed an input Z here. When there is an first input Z, and here your aim is to predict the next character. So if you have to predict the next character, when there is Z, what are the probabilities that you get the next? It can be ZE, or it can be, if it is zip, ZI. So here you have in order to predict the next one, it is depending on the previous input. So when you just have Z, the possibility of next word, next character are many. So now for Z, when you give E, then the probability or the possibility of having the next character is B. So what you are going to predict next actually depends on the current input and then the previous also. Now what do you mean by this? When you have a current input as E and the previous input is Z, then the possibility of you predicting the next is B. Right. So here also the every input is actually depending on the previous, and the order of input matters here. Now what do you mean by order here and depending on the previous, what exactly? Now if you look into you have ignored the previous. What is previous? The previous was Z, now you have ignored that Z. What is the current input? The current input is E. Now when the current input is E, what is the next probability? What is the next? If the first character is E, the next can be anything, eating or elephant, EL. The possibility of next are many, but if you consider even Z, you can able to predict if when the current input is E and if the previous input is Z, then the next can be B. So here when an application, what kind of application it is? It is an text application where you are predicting the next character. And what exactly the model will do? The model actually remembers the next, or here the model is actually remembering the previous input. Therefore input is not independent anymore, and the order of the input really matters in such applications. This is what is one application. Let's look into one more very popular one called Google Autocomplete. When you look into this is an natural language example, Google search autocomplete. Here when you just type only deep, the suggestions are different. The minute you press L, you type L, again the suggestions are different. So when you complete deep learning, then again the suggestions are different here. When you give ease, the suggestions are. So here the model cannot generate the next word without actually knowing what was the earlier words in the sentence, right? So this example again shows there is a dependency between the inputs, and then the order of the words actually matters here. Let us continue with the next example. So let us see punching, this is an punching one. If you forget the entire sequence, if you look into only one frame, I am just focusing only on the first frame. Now if there is only one, if there is only this particular image, from this we really cannot understand whether the first person is calling the second person, or whether the first person is just touching the second person. We really does not understand anything just by looking at one image. Now from here, the similar way, if you look into each of this image, now when you look into this, we really doesn't know whether a person pushed or whether a person punched or whether a person took his hand to shake the other person's hand. We really does not understand anything just by looking at a single image. So a single frame has no meaning. The action that is being performed here can be understood from a sequence of frames here. So here again there is a dependency between the inputs, and then the order is very important. Let us move into the next example. When you go for speech to text one, when you are speaking, whatever the word that you are speaking actually depends on your previous words. Similar way, when that speech is converted into a text we have seen from this that whatever you are typing actually depends on the previous one. So speech to text, here also in the input there is a dependency between the inputs. All these examples what we have seen, they are called sequential learning problems. What do you mean by sequential learning or sequence learning problems? There is a particular sequence in order to predict something, or there is a sequence involved. Here there is a sequence involved, there is a sequence involved, there is a sequence involved. So all these are sequence learning problems, and the characteristic of the sequence learning is the order of the input really matters here, and the current input depends on the previous input, and the input length is not fixed. What is the meaning of input length is not fixed? When you look into deep, the word deep is just 4 letters. When you take learning, it is of a different length. When you take ease, it is of different length. So here the input length is not fixed. So if at all, if you have an applications of these kind, can we use ANN and CNN here? Answer is no. Why? Because ANN and CNN works, its requirements we have seen in the previous slide, where there is absolutely no dependency, and then always the input size should be fixed. There is no dependency. But here, if these kind of an applications you take, there is a strong dependency. That is the reason why ANN and CNN structure fail in on sequential learning problems. If this is the case, we definitely need a model to be built. Now we need to build the model for such applications. Now what are our requirements? That model should take care of what? The model that we are going to build should definitely handle the dependencies between the input. Yes, and any input of any variable length, the model should be able to handle it. these are two important requirements that we have. Those two important requirements are input should strongly depend on a previous input. So, there has to be a dependency between the inputs, and the model that we are building should be able to handle any variable length inputs. In order to achieve these 1 and 2, what this model has to do, at each time step, whatever the function that is executed by the model should be the same. So, this is very important. At every time step, whatever the function that is executed by the model, it should be same. Now, let us try to understand this with an example. Now, this is an sequential data that we have built. This is one sequential data where our aim is to predict Monday. So, shopkeeper wants to predict what is the sales for Monday. Now, the very first step is, since here the input values are of variable 1, some values are very small, some values are very large. So, we are first going to normalize it. How is that we are going to normalize? It is a fundamental concept from week 1. So, you will take from this whole, the minimum value is 6 and the maximum value in this entire is 12 and the minimum again is 6. So, first what is x? 9. So, 9 minus 6 divided by 12 minus 6, whatever is the value, put that value here. Then in the place of x, take the next number. So, here you change the number to 7, put a 7 which is the next number, 7 minus 6 divided by 12 minus 6, put this. So, normalize each of these values. Once we normalize, look at this particular problem statement. What is the problem statement here? When you have the data for Monday, your requirement is you have to predict Tuesday's data, right? This is what is sequential one. When you have Monday's data with you, the requirement here is you have to predict Tuesday's. Now, when you have Tuesday's data, the requirement is you have to predict Wednesday's. When you have Wednesday's data, your requirement is to predict Thursday, and so on so forth. When you have this particular data, your requirement is to predict this. So, this is what is the problem statement. Now, when you have Tuesday's data, when you have this particular data, when it is predicting Wednesdays, okay, when you have this particular input, it is its aim is to predict Wednesdays. Along with that, it will also look into what was the previous one, right? This is how the application works. So, if that is the case, can we create a data set something like this? What exactly? This is a normalized values of the original value. When we have Monday's data, the requirement is you should predict Tuesday. What is Tuesday's value? 0.17. When you have Mondays, the prediction value is this. When you have this particular value, the prediction should be Wednesday. So, if this is x, this is y. If you have Wednesday's data, you have to predict Thursday. So, this becomes your y. When you have this data as input, you have to predict this, which means this value is y. So, have you understood how, I hope this is clear, how we have created this particular data. So, once you have this, now you need to build the model. Now, let us look into only this. You have one input, so and you have to predict one output. So, can we build a model something like this? So far you have seen that the model will be built something in this way. You have an input passed to hidden layer and then there is an output. So, at a hidden layer there is an summation and then activation. Here also there is a summation activation. This is how you have seen the model building so far. Now, the same we are writing in this representation. Why we are writing, you will understand this in a while. Now, when you take this, when there is an input x1 that is passed, is it not you will have an weight here and there will be an bias term here, and you do some computation, and once you compute you get some output, that output you will multiply with this weight and there is a bias term. So, similar way, when you have a connection something like this, is it not we will have an this weight and bias here, and this weight and bias here. So, we have built a model this. For what you have built for this. There is one input and there is one output that you want to, so you have built this. Now, what is the next step that you are doing? Let me erase what is not required. Okay. So, all this we have already seen it in the previous one. Now, let us see, you are passing, this is the first input that is passed to the network. Now, you are taking this second input. What is the second input? This is the second input 0.17. Now, when you are passing the second input 0.17, you have to pass it to the neural network only. Now, to which neural network you will pass? You have built this neural network. If you have built this neural network, you will pass to this network only. So, can we draw this diagram, because anyhow you are passing to this right. So, we have redrawn this, and to this you are passing 0.17. Please focus here, it is 0.17. Now, when you pass the next input, now what should be the values here? So, again you will be having some weight and bias, here also you will have a weight and bias. Now, can we use the same weights what you have used before? Can we use the same weights here? What do you think? What should be the answer, whether it is yes or no? The answer is yes, right? You will be using the same weights. Now, the question comes, why are we using the same weight and bias? Why have we not, why is that we, why cannot we use an other weights? Look into this concept. What is our requirement? At each time step, the function executed by the model should be the same. Now, what is the function executed by the model should be the same here? What is the same? The same here is weights and bias. Therefore, at every time step, what do you mean by at every time step? First you are dealing with this, second you are dealing with this input, next you are dealing with this. After you complete all of this, then only you will predict the next one, right? So, at every time step, the function, whatever the function executed by the model, we have still not discussed what function, but should be same. This should be same is the same weight and bias. Okay. Now, there is one more interpretation here. What is that? Now, for the first input, you have passed x1 and bias 1. For the second input, if you use a different weight W2 and bias 2, suppose if you use a different weights, what exactly is happening? How many weights you have considered so far? You have considered 2 weights. Now, let us assume you have a length of 4. So, you are for the third input also you are using one more, for the fourth input also you are using. So, how many weights you have used for this word? You have used 4 weights. Now, during testing, let us assume you have got next. You have got the next character. Now, when you have the length as 5, how many weights that you have learnt only? During training, you have used only 4 length. Therefore, you have learnt only 4 weights. But during a testing, what if you get the different length? Then the model cannot ideally work, right? So, that is one more reason you cannot afford to have different weights. So, you are retaining the same weights. So, this is the meaning of should be the same. With this, out of these 2, which requirement is taken care? Any length, the model will be able to handle it. correct. Now, let the input be of any length, the model will be able to handle. Why? Because you are passing everything to the same one, where the weights and biases are the same. Now, to the same you can pass the first input, second input, third input, length of 100, length of 1000, whatever. Yeah, since the parameters are same, the variable length inputs are taken care. I hope this point is clear to you. Next, you are passing the next input. For the next input also, since should be the same, you are retaining the same weights. Similar way and go so on. Even for the last input, when you are passing the last input here, still the weights and the bias you are retaining the same. With this, you have achieved any variable length. So, this point is taken care. Now, let us see what is the function that is executed. Now, how will you write this equation H1? This is summation and activation. What is this summation? Is it not H1 is x1 Wx plus b? And this entire is then passed to an activation function, and since we are dealing with RNN, the activation function what we use is tan h. So, H1 the equation is tan h. To this you are passing x1 Wx plus b, and that b is this, right. This is an function that is executed. So, and similar way, what is y1 hat? Y1 hat is h1 which is multiplied with the weight and then bias. H1 multiplied with the weight and then the bias. What weights? Weight at an output. Now, that entire here also you will have summation and activation. So, that entire is passed to an activation function. F here is an activation function, and that activation function is an output activation based on what kind of problem you are solving. Suppose if it is a regression problem you are solving, then this F will be a linear activation. If you are solving a classification problem, this F will be a sigmoid, and accordingly what kind of problem that you are solving, this F is an output function. So, similar way, look into what is the function that is executed at H2. It is the same values, second input, but the values are the same, the parameters are the same here. So, in general, can we write this? Some input multiplied with the weight plus bias Hi, and this is the function that is executed. So, at every time step, the function executed by the model should be the same. What are the functions that are executed? This is the function that is executed, and what is the meaning of same? The weights and the bias should remain the same. Why weights and bias should remain the same? Which parameter, which constraint you are taking care? You are handling this one. Any input of variable length, you are handling it. Okay. So, I hope this is clear to you. Now, the next important, have you completed this? We have still not completed because handling dependencies between inputs is not completed. So, let us see how to now look into handle dependencies between the input. So, this is the from the previous, for the first time step, when you pass the first input, you are executing this. When you pass the second input, you have to retain the same. So, we have retained the same weights and bias. Now, it has to handle the dependency. Dependency meaning when you are processing H2, what is H2? H2 is the neuron which is processing the current input x2. When H2 is processing x2, it has to look x1 also. It has to look into previous input. That is all about sequence models, right? When you are processing the current input, it has to look into the previous input also. Now, what is the previous input? The previous input is x1. So, there are two ways that you can reach to x1. One, you can reach from this. First from H2 go to H1, and H1 is having this x1. So, one way of reaching the previous input, that is x1, is this. this is how you can reach the connection from H2. H2 when it is processing the current input X2, H2 should look for X1. So, now if H2 needs X1, it can one way is first H2 go to H1 and H1 is anyhow having X1. How? H1 is nothing but X1 multiplied with the weight and then the bias. So, H1 is having this X1, right. So, because you have established a connection, there is an weight associated with it. So, there is a weight WH. Now, the most common question everybody gets here is, why not use directly? Why not pass directly to this? H2 needs X1, right? If that is the case, why not have a direct connection like how we have shown here? Why not use a direct connection? So, can you think what it is violating here? If you have a connection, there will be some weight here. When there is a weight, is it not the function executed by the model should be the same each time, it should be the same. Where is the same here? For X2 you are using this weight, for X1 you have changed the weight, right. So, that is the reason you cannot directly establish the connection from X1, you cannot directly go to H2, you cannot, you can reach from this way. I hope this is clear to you. So, similar way, now you pass any number of, you are now passing the next input. When you pass the next input for H3, what is that you should consider? You should consider all of the previous inputs. If you have to look into all of the previous, you need to establish the connection. So, there, when you establish a connection, the same is retained. Now, when there is now for H3, when it is processing the current input X3, it is looking into H2 and H2 through H2 you are getting X2 and which in turn it is looking into X1. So, is it not we are looking into all of the previous samples also? So, this is what we cannot do, this we should not do. Why we should not do? For every of the connection, if you directly establish a connection here, so from X1 directly if you pass it to H3, X2 if you pass directly to H3, for every connection, for every new connection there are weights that are associated, then the model should be the same, that rule is violated here. So, this is not the correct way of doing, this is the correct way of doing it. So, let us continue. We will continue with all of other inputs. So, finally, we are going to get this. Now, let us look into, now in the previous slide we have only seen a variable length input. Now, for this where there is a connection also, how do you write a function? Let us first write a function for H2. For H2, is it not X2 getting multiplied with this weight and bias? Is it not X2 getting multiplied with weight and bias? And for this H2, is it not you have this connection also? What is this connection? H1 getting multiplied with the WH, H1 getting multiplied with the WH. So, that is what is H2. With this we will also write H1, we will do it. So, I hope H2 is clear. Similar way, what is Y2 that we are writing? Y2 is a direct function. So, some activation output activation function, for that H2 gets multiplied with this weight and then the bias. So, can we, if this is the equation, now when you write H3, H3 is the previous, H2 gets multiplied with this and rest everything will remain the same. So, now with this can we write what is for H1? H1 is can we see H1 is just X1 getting multiplied with the weight and then the bias. For this H there is nothing from the previous. So, when there is nothing from the previous, ideally this H naught is 0. When this is 0, this whole term becomes 0. When this whole term becomes 0, for the first time the calculation is just only this, right. So, in general, how will you write? So, in general you are going to write it as when you are at H3, you are taking H2. When you are at H2, you are taking H1. When you are at Hi, you are taking the previous I minus 1. I hope this is clear to you, and then the activation output 1. So, what we have this is now the total function that is executed by the model, which is actually taking care of point 1 and 2. Both the points it is taking care. Now, we are combining everything together, and this is what is the compact representation. Can you see this? What did we do? Whatever is the connections we have written in this way. So, this is a compact representation, and the connections, intermediate connections what we have seen, this is a recurrent connection in the network. So, this is what is RNN architecture, where it is now handling the dependencies between the inputs, how it is handling the dependencies because of this connection. So, through this connection you are reaching the previous input also. And variable length inputs, how are you fixing the variable length inputs? So, that each time when you are taking the same parameters, now execute any number of, let any number of input being passed, it can able to handle it. So, with this you can able to handle any of the sequential examples. So, let us come to the last topic for today's session, which is the types of RNN. So, we have 4 different types of RNN. One is one-to-one. What is one-to-one? It is the most basic configuration of RNN, where this is required to understand the next complex variants, where there is one-to-one meaning, where there is a single input and you get the single output. So, what are the different examples for one-to-one? Can you pass some temperature at a time t, so that you will get an output at a time t plus 1? Right? You can pass one single image and you will get what is the name of this particular image, sunset. So, one-to-one is there is a single input and you will get a single output, one input and one output. Next, we have one input and many outputs. So, is it not one input and you have multiple outputs? So, we will say that it is one-to-many. What is one to many? One to many is also called as generative mode or generation mode. Now, what exactly is this? You just have only one input. From this one input, you know that you get the one output. That is not a problem. But with this, you have to get an output with each of this with just one input, right? So, it is also called generative mode, and here there is a small change in the mathematical working. Look at this small change. For the first one, there is absolutely no change. When you pass the first only input, x1 gets multiplied with its weight and then the bias, and this is your h1, that is summation, and you have weights at the output, and then the so you are passing. This is a simple one, but when it comes to h2, for h2 definitely the input is this. You will have some weight, you will have h1 multiplied with the weight. So, for h2 you will have some function, and that is where you are passing this. But along with this you are also passing, look at this, what for h2 what is that we are passing? We are passing the previous one. Along with this, whatever the output that you have got when the first input when it is passed, whatever the prediction that is made, that is also passed as an input. So, when there is a connection, you will have a weight there. You are also passing, you are passing the output of that to an input. Now comes the important one, why you have to pass the output here. So, this is a little different from our RNN mathematical model. So, here the output is being passed, because we are interested, this since it is an generation 1. So, during a generation we don't we just need the continuity in the output. We really no need to remember anything about the input. So, if it is predicted something I, so next time it should predict I am. I just want some continuity in the output. So, I am looking only at the output, but not at the input for H2. Therefore, the mathematical formula for one to many slightly differs here. You can see the output of this is passed as an input. So, because there is a connection, there is a weight also. So, what all different inputs examples. So, this process continues with this. So, we get a sequence of outputs, even though we just started with one input. Pass an image. So, I am just passing one image and I am getting a sequence of outputs. A boy is playing football. So, what exactly is this? Is it not image captioning example? Then I just pass text generation, storytelling. We are passing a single word called friendship, and I am expecting it to give a story. Once upon a time, two friends, and so on and so forth. You just pass one input, but you get multiple outputs. So, this is story generation, where a single word is passed as an input and you get a sequence of words as an output. So, this is one to many example. Then what exactly is this? We have multiple inputs, many inputs and one output. So, many to one. So, this is a good example, and where you are passing multiple inputs, and towards the end of this input itself only we are understanding that it is a Surya Namaskar one. So, I am giving a credit for this example, I am giving a credit for this course. So, when you have passed a sequence of inputs and you are getting one output here. So, this is a many to one, and towards the end of this only we are understanding that it is a Surya Namaskar. So, this is action prediction, and the second, you are passing a sequence of words. Look into this, the movie was very good. So, what is the output that we are getting? We are getting a sentiment analysis. So, we are getting an output, it is positive. So, sequence of words is passed as an input, and the output what we are getting is a sentiment. And the last variant what we have is many to many, many inputs and many outputs. So, what are different examples can you think of? You are doing a great work. So, you are translating it into some other some language. Here we have translated this into Hindi. So, here multiple inputs, multiple outputs. So, in mission translation we are using many to many model. Then here it is once again sequence of video frames, and what we are getting is for every video frame you are giving the name to it. What is the name of this asan? What is the name of this asan? So, we are getting a sequence of words also. For every video frame you are getting a caption. Children play outside every evening. So, now what is that? Children is a noun, and play is a verb, and outside is an adverb. Then every is an determiner, and evening is a noun. So, what exactly is this application? It is part of a speech tagging application. So, all these are the different variants of CNN. So, with this we have come to an end of this particular session, where we have seen why ANN and CNN fail for an sequential data, why sequence, what sequence learning problems need, and then we have explored the RNN architecture and the types of RNN. And in next session we will solve one numerical example on RNN, where we will understand the forward computation. We will see from input to hidden and from hidden to output. Thank you.